let's go over these questions. And there's that activity series, and you're going to see why we need this. So the first thing we need to do in all of these questions is you have to identify the type of reaction, right? And so sometimes with the words, it's sort of hard to do. And so when we do that, let's just write this out. So sulfuric acid, perfect example of what we need to be doing for our first exam, right? So sulfuric acid, H2SO4 plus zinc, right? And so you can see the first thing you have to do, remember, is to classify the reactions. And this activity series will be provided for you on the exam. You do not need to memorize it. You never need to memorize it. I'm using the exact one that I put on your exam and your quiz and your final. So you're super used to using it. Okay, so we know that this is a single displacement, right? Now, why is it a single displacement? What's the key? It's all by itself, right? This zinc, it's a compound and then one element all by itself. That's how we know it's single displacement. And so why is that important? Because that tells us where to look, right? So if we look here, I know you probably can't see this on here, it says single displacement. And then it says literally see activity series, right? So it says see the activity series. So that's our hint. Oh, why do we use the activity series? We only use it for single displacement reaction. That's it. That's the only time we use the activity series, single displacement only. So our question is, can zinc kick out hydrogen? Remember, if zinc's above hydrogen, it can. Here's hydrogen, here's zinc. Zinc is above it, it can kick it out, right? So that means this reaction will occur. So when we write this, that means that we're going to have hydrogen all by itself, and then zinc will be with sulfate. Okay, that's our next step. Yeah, and this sheet, by the way, you get to use this exact sheet for your exam. So the one that you printed out and you're using for your homework and during the lectures, you get to use this sheet for your quiz and your exam. Okay, hence why, and it's literally, I give you the exact same. Actually, this one I don't put on the exam because then it's like pages and pages that you have to scroll through. So I just trust that you will have this written or printed out for your exam. Remember, if just as a side note for your quiz or exam, you can't have anything else but what's already printed on here. So if you have like scratch writing you've put on here, you need to get a fresh one for your exam and for your quiz. Okay, so now we have to learn
H2.
Yes. So our next thing we have to do is we need to check and make sure all of our charges are balanced, and we have to think about our Brinkelhoffs, right? Hydrogen is a Brinkelhoff, so it needs to be 2. Then we need to check our charges for zinc and sulfate. So remember that zinc is a +2, sulfate is a -2, and we're all good. Now, if we don't remember that zinc is a +2 and it's a -2, I don't have a periodic table with me, so I'm just going to write on mine right now. So I did it in pencil. Remember, these 3 are +3, these 2 are +2, and that 1 is a +1, right? That's that little triangle. You can write that on your exam, on your periodic table for your exam. Remember that. Okay, so now we've got this. We're good. Now we have to make sure it's balanced. Right, that's our next step. We have to balance our reaction. So looks like we're set on that part, right? It's all balanced. Okay, then we have to do our states. Acids are always AQ. Remember, AQ just means dissolved in water. Zinc metals, remember, are always solids. Hydrogen is part of Brinkelhoff, so it's a gas. And now this, because it's in this acid, which means it's in water, this will also be an AQ, right? And we're going to talk more about how you know that today. Okay, let's do the next one, silver nitrate. I'm just going to assume, by the way, that we all know this, right? That's exam 1. And then that was supposed to be an arrow.
Dr. McAdam?
Yes.
I have a question about the exam for these.
I was going over the practice review last night, and I noticed that you put AQ on some of them for the answers. Did you want us to do that on the exam as well?
No, you don't have to do the states for the exam just because we haven't, that's really this. So they're there, but they're not mandatory yet.
Okay, thank you.
So after this module, then we're going to really be using those a lot, but not yet. Okay, so now this is a double displacement reaction, which we haven't really gone over of how to do these, but we've seen them. So remember, the key on double displacement, which we'll talk about today, is whoever is first always stays first. So AG has to stay first. H has to stay first. Oops. The other two are going to switch places. Right? So this is going to be AgCl, and this is going to be NO3, right? And so again, now when we do this question, we're going to kind of further we're going to further go over this one in just a few minutes when we do this. And again, now it's balanced, we're good. So we'll go over that one in more detail in a few minutes. The next one, calcium oxide. So this one is kind of a special one, right? So this one's actually a combination or a synthesis reaction. And this one is a special one. And again, if we look at combination or synthesis, this one is third from the bottom. Metal oxide plus water makes metal hydroxide, right? And so it's the third from the bottom on your combination synthesis. So that's the reaction that we're going to use. And so when we do that, we get a metal hydroxide, but we have to balance this, right? So we need to balance this because calcium is a +2. Again, this is our exam 1 review. OH is a -1. Remember, we can't just put a 2 here because then that looks like there's 1 oxygen and 2 hydrogens. Now we have 2 OHs, so we need to put a parentheses, right? And then after we do that, we look and say, okay, we need to balance it, and it's balanced, right? So this one, ionic compounds are a solid. Water is a liquid, remember? There's very few liquids. We have water, mercury, bromine. There really are only like liquids unless we have something like molten, like lava, right? Like molten metal. And then because this is in water, and again, we're going to develop this soon, this is going to be AQ. And again, this one, we're going to learn about this one in greater detail.
Professor?
Yes.
For the silver nitrate one, with the products, would they be AQ too, or?
These we're going to talk about. That's what we're going to be doing today. So what the actual states are of those. Technically, yes, these would be all AQs. But there's a little special thing we have to do with these double displacements. But these are actually all AQs. So it actually ends up being no reaction. But again, we're going to talk about this more in just a few minutes. But great question. Okay, aluminum oxygen. That sure does look like a combination reaction to me, right? And if you only have 2 elements and they're combination, you have right there the very first one. Most metals react with nonmetals to form ionic compounds. Aluminum is a metal, oxygen is a nonmetal. This is rule number 1, top of the page. So we put those together. But remember, this is what I see all the time. People are like, oh, there's a 2 there. I'm going to put a 2 there. No. The reason this 2 is here is because this is a Brinkelhoff, right? And that's why it's diatomic. These 2 sides are separate, right? We don't bring any of those coefficients over, or these subscripts, we don't bring any subscripts over. We need to balance our charges, just like we did for exam 1, +3, -2. So this is a 2 and a 3. And then our states, metals are solid. This is a Brinkelhoff. This is an ionic compound. Doesn't say anything about water, so this must be a solid. Okay, our next one, potassium chlorate. Again, I'm gonna write this over here so it's not so far down to the bottom. That's potassium chlorate. Hopefully, we're all good with this. This sure does look like a decomposition problem to me, right? And so then we have to look at our little sheet, decomposition. I'll look at the second one. Metallic chlorides decompose when heated to metallic chloride and oxygen. Okay, so that means metallic chloride, our metal is K, Cl is a chloride, and it says metallic chloride and oxygen, right? And then we're pretty good with this now. That's a Brinkerhoff. Check our charges, +1, -1. We don't need to do anything here, but we do need to balance it. I sort of left enough room to do this. 3, 2, 2. And this is an ionic compound, so it's a solid. Ionic compound, so it's a solid. Brinkerhoff, so it's a gas. Okay, next one. Potassium bromide plus chlorine. And remember, chlorine is a Brinkerhoff. This means when it's by itself, there are 2 of them. Now for this one, this is a single displacement. How do we know? Compound, 1 element. So this is a single displacement reaction because it's a compound and 1 element. So in this case, a lot of times I see people try to have the K or the Cl replace the K, right? Remember, this is the positive one, this is the negative one. Chlorine as an ion is a negative. Negatives only replace negatives. Or think of it as nonmetals only replace nonmetals. Metals only replace metals. So in this case, what we're asking is if chlorine can kick out bromine. And in order to figure that one out, we have to look at the periodic table, right? This one's not on your activity series because remember, this periodic table is like, see, it is like a little activity series. And so the higher it is, the more active it is. So since chlorine is above bromine, that means that it can kick it out. So that means poor bromine, it's all on its lonesome. And chlorine gets to be with potassium. But again, Brinkerhoff, 2 of those, right? Okay, so now we do our states, ionic compound, Brinkerhoff, gas. Our exception to the world of Brinkerhoff, liquid, ionic compound, solid, right? And then, oh, I forgot to balance. 2, 2. Okay, so this is exactly what we're going to do for your next quiz and your next exam. You're just going to be doing this again and again and again and again and again and again, right? This is exactly what you're going to be doing in your homework and when you're doing your OLI, right? The key is to be able to classify and then be able to use this sheet very, very efficiently. And again, this sheet you can use for your quizzes and your exams, but it needs to have no extra writing on it, right? So you can't have like hints and things on this. It can only have what's already written on it. So if you have been writing on it, that's totally fine, but you can't use that for your quiz or your exam. You need to have a new one, or if you don't have a printer, a cleanly written one. Okay, so now let's talk about double displacement in more detail. So double displacement or double replacement, whichever, is when they switch partners, right? We get 2 new compounds. So there's 3 real different types of double displacement. You can call them double displacement or you can be more specific. Either of those are okay. So we have precipitation, we have gas forming, and we have acid-base neutralization reactions. So we have all these different 3 things, but they're all in general called double displacement reactions. They just have more specific names. Okay, so here are some examples of double displacement reactions. And double displacement is on the back of your sheet. So we have acid-base neutralization. And an example of this, acid plus a base makes salt and water. Remember, a salt is any ionic compound. It just happens to be table salt is an ionic compound. We just call it salt, but any ionic compound is called a salt technically. So if we look at this, Here's hydrochloric acid, sodium hydroxide. It actually makes, in this case, table salt and water. Here's another example. Here's a metal oxide plus an acid, and again, it makes a salt and a water. Oops. So metal oxide, here's our nitric acid, right? This is copper 2 nitrate, right? Because copper's in the middle. Copper 2 nitrate. Copper's in the middle, so it needs those Roman numerals. And then water. Okay, so now, when we're doing these double displacement reactions, you're going to see that we have the AQs, which means they're in water. So pretty much all of our double displacement reactions that we're going to be talking about are in water. Remember, in water means AQ. So in this case, we're going to have this mixing with this, and it makes a solid. And we're going to talk about how do we know this makes a solid in just a minute. How do we know that that is an S? We're going to use this thing called a solubility table. Here's an example of a gas forming. Here it is, this gas. Again, we're going to talk about how we know that's a gas in just a few minutes. And then we can have what's called a secondary reaction. And so here's our first double displacement. And this further breaks down into these two things. And again, forms a gas. So we're going to look at all of these reactions and figure out how we can determine what's going to happen. Okay, so here are your double displacements. I think there's actually a missing one. I'm missing the metal oxide one. Metal oxide plus acid makes salt and water. That's on yours, but not on this one. I just obviously cut off the back or the bottom of it. Okay, so now let's first talk about precipitation reactions. For precipitation reactions, and really honestly for all of your double displacement reactions, you're going to see, I'm going to show you this again. I know it's backwards. Double displacement, right under it, it says see solubility table. Just like single displacement told you to see activity series. It's telling you where to look, right? This solubility table, you're going to have on every quiz and every exam. You don't need to memorize your solubility table, right? This one is the one I put on your quizzes and your exams. Yes, this is the one that I put on your quizzes and exams so you can see it. I'll use a couple other ones. There's so many solubility tables out there, but I wanted you to see and become familiar with the one that you're actually going to be using. Okay, so now the question is, this is a double displacement reaction. How did we know that that's a solid, right? So this S, that is this white stuff, right? So we use the solubility table. So we look here, and we just look for, usually I think the easiest way to do this is to look for the anion. That's just kind of the easier way. So I'm just going to look for the word sulfate, and I'm going to keep just going down. No, that one doesn't say sulfate, doesn't say sulfate, doesn't say sulfate. Oh, that says sulfate. So I'm going to look at this rule a little closer. It says all sulfates are soluble. Soluble means AQ, right? Insoluble means solid, right? A precipitate is a solid, okay? Okay, so sulfates are soluble except barium, strontium, or lead. So that means they're all soluble except for, meaning these make solids. Whoop, there it is. That's the barium sulfate. That's why it's a solid.
Could we write what you just wrote on there on our paper?
All you need to do is put the S.
No, but I mean like on our solubility rule thing, our Chem 209 reactions paper.
Oh, this I'll actually put on the top of the quiz for you and the top of the exam. So you don't need to put that on this paper.
Okay. Thank you.
Same thing with the activity series. I'll actually put those with the periodic table on the top of the exam. So you don't need to worry about those. Okay, so if we look at what happens here, we're going to talk about what aqueous means and what happens. So this barium chloride is going to separate into Ba2 plus and 2 Cl minuses. right? So I'm going to actually expand this a little bit more. And this skill right here, if anybody's going beyond 209, is extremely important in 219 and in 229. So BA2 plus, how do we know it's BA2 plus? A couple different ways. It's in group 2, so it's +2, right? Or flip it up, +2. Chlorine is in group 7, so it's a -1. So there's 2 chlorine, so I could write Cl minus plus Cl minus. Well, an easier way to write that is just we have 2 Cl minuses, right? So I just went straight here, right? So these become ions, means they're just kind of floating around. And we're going to talk more about this in just a second. This Na and SO4, we're going to make 2 Na pluses and 1 SO4, 2 minus. They're going to become ions. But this is not going to come apart. It's going to stay together. It's not going to make an ion. So when you see this AQ, know that it's going to come apart, right? This also is going to come apart. It's going to be floating around. So you see these ions I have, like these pictures where they're just floating around here. There are ions floating around, but this stays together, right? This solid piece stays together and it doesn't come apart. Now, how do we know that? Someone did a ton of experiments for us and figured out our solubility table, just like they did the activity series for us. Okay, here's another solubility table. This is my favorite one, but the chemistry department doesn't like us to use it because then you don't need to know your polyatomic ions. I think that's why I like it, because I know here, like, watch, this is why it's lovely. You're like, oh, NO3-, it says nitrate. Oh, it says acetate. It's a handy dandy one, but we're not supposed to let you use this one. But this is my favorite solubility table. So sometimes I'll use this. But how do you know if it's soluble or insoluble? Insoluble means solid, or it'll say precipitate, PPT. Soluble, remember, means AQ, comes apart into ions, right? That's what it means. It comes apart into ions. So this again is just, I have a couple of different solubility tables here so you can use, just so you can see. Again, there's so many of them. So how do we know if it comes apart into ions? Again, if this comes apart into an ion, that means it comes apart like this. Right? So the question is, does it come apart? Does it come apart into ions? Is it aqueous? So we just look. This one's kind of cool. The whole top is soluble, the whole bottom is insoluble. So we look, it says nitrates, soluble. Remember, soluble means AQ. And then we look here. Sulfate, soluble except there's that exception, right? So you can see I have 2 different charts here, but they give you pretty much the same results, right? It just kind of depends. This again is the one that you're going to see on your quizzes and exams, so I'm going to use this one most often. All right, our next one. We see chlorides, bromides, and iodides, meaning they are soluble. So this would be AQ/soluble. Okay, so now let's look at what I was talking about on that they come apart. So here's lead. I'm going to help you, right? Studying for our quiz here, or our exam. This is not lead nitrate, but lead 2 nitrate, right? Because again, you could flip it up. Makes nitrate a -1, or you could do the algebra way. But this is lead 2 nitrate. Now, it is aqueous. If you look at your solubility table, it says it's aqueous. The one I tell everyone to memorize is the one that says all nitrates are soluble, because that one's like the easiest one. So it means if you see a nitrate, it's AQ. Again, AQ means it comes apart into pieces. So that's an AQ. Now, potassium chromate, again, if we looked, we would see it's also an AQ. Again, that means it comes apart into pieces. The question is, when we mix these 4 pieces together, will they combine to make a solid? So if we put them together, will these combine to make a solid precipitate? So we know that's not a precipitate, right? Because I told you that one, all nitrates are soluble. And this one's not a precipitate because I just told you it's not. So the question is, Is that a precipitate? Well, that's a nitrate. All nitrates are soluble. How about the lead chromate? I don't know. We have to look. But if one of those two combinations is insoluble, remember, insoluble means solid, right? Then we have a new product. So let's look. So again, we're going to, now watch here what I'm going to do with the last two pieces right here. I'm going to have them switch, right? That's how you do the double displacement reactions. So a lot of times people are like, well, who goes first, who goes second? Just notice this is always the positive ion, negative ion, positive ion, negative ion. So it stays positive ion, negative ion, positive ion, negative ion. Positives always go first, right? It doesn't matter if this comes before this, that doesn't matter. As long as whoever is positive is first. Or you think of it as whoever is a metal is first. It always goes metal, non-metal. Okay, now we look at we have to look at a solubility table, which I guess I used this one this time. So we know nitrates, all nitrates are soluble. So we know that's an AQ. But if we look at chromates, here again, this one says insoluble. This says it's insoluble. Remember, insoluble means a solid. And that's an aqueous. So this would be solid, AQ, 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 right? Well, this means this one does not come apart. It sticks together. So if you made this in the lab, you would just have this sitting at the bottom of your solution. It would just sit at the bottom. Nothing would happen. It would just sit at the bottom. And the rest of these would just be floating around as ions. Okay, so let's try another one. So we have sodium chloride and potassium nitrate. So again, just watch here. I'm just going to flip these two, right? And then we check our solubility table. So here's a solubility table you're given. Remember, I told you just memorize that one. All nitrates are soluble. So this is aqueous. Told you that one, right? Just remember that one. This one, again, it helps, I think, to look at for the anion. So we just look for chloride. Doesn't say chloride, doesn't say chloride. Oh, here's one. All chlorides, bromides, and iodides are soluble except silver, mercury, and lead. Well, that is neither silver, mercury, nor lead. So this is aqueous. And so nothing was formed, so no reaction actually occurred, right? So the answer to this one is literally no reaction, right? And so all we do is we just have a bunch of ions floating around, but nothing was actually made. So no reaction occurred. So if you had these two compounds and you put them in a solution together, you would see nothing. Nothing would happen. You would just have a clear solution and a clear solution, and you'd mix them together and you'd have a clear solution. Nothing happens. And so we can just write no reaction.
So the reason it's a no reaction is because they're both aqueous?
Yep. Yeah,
Okay.
they're all aqueous. So when this comes apart, so when we put this, so kind of like to use the little cool little example I had, this is Na plus, this is Cl minus, this is K plus, this is NO3 minus. They're all just bouncing around the beaker or the cup. They're not actually together. We write them together, but they're actually apart. So when we mix them together, they're still all apart. Like nothing new was formed. They're just still over here, just bouncing around. Just the four ions are still just bouncing around, not doing anything. So for a precipitation reaction to occur, you have to have a solid, right? You have to look at this paper here, and one of them has to be insoluble. Remember, insoluble means solid. Okay, so now here's one. This is like an example that you'd see on a quiz or exam. I am telling you, we're going to have a precipitate. Something is being made here, right? So we have, it says a precipitation of a white solid. So there's definitely an insoluble thing happening. Silver nitrate and sodium chloride, right? Again, this is why exam 1 is so important, our elements and compounds. Silver nitrate, there's those polyatomic ions never leaving our chemistry, plus sodium chloride. And now, I didn't leave very much room, but that's okay. I'm just going to leave silver first, and I'm going to leave Na first, and then I'm going to flip the second two. Na, oh, I flipped it wrong, sorry. I need to write this, I need to write it neater. It's very distracting when it goes over that. I'm gonna write this much neater. Okay, silver nitrate plus sodium chloride. There we go. Silver plus Na. And so our silver is gonna go with our chloride and our sodium is gonna go with our nitrate. Now, that plus looks very bad, sorry. Now, we're gonna look at our solubility table. Okay, so remember, all nitrates are soluble. Oh, I did not leave enough room for the AQ, so I'm gonna put them under it because I didn't leave enough room. So AQ, all nitrates are soluble. AQ, right? Just remember that one. Chlorides, soluble, right? We just did that one right there. We need to decide this one. Chlorides are soluble except silver, mercury, and lead. We have silver. So that except means that it's a solid. Because remember, soluble is AQ, except that means it's insoluble, so it is a solid. So this white here, this is silver chloride. That's what this is. It's silver chloride. It doesn't come apart in water. It's stuck together with the silver and the chloride are all stuck together. Okay. Here it is neater. Again, there's that flip. And I use this solubility table this time just because I like you to see other ones. Aqueous, this is our solid. So this would be our reaction, and it's balanced, so it's an easy peasy nice reaction. So for a precipitation reaction, go ahead.
What slide are we on? I'm kind of lost when it comes to the notes because mine doesn't look anything like yours.
These animations aren't all on your slides because they're just extra things, the animations.
Yeah, I don't know the animations, but like I don't see a page where it says precipitation reactions and then a point.
So they're not all on there. So sometimes there's more, sometimes there's less. If you ask in the chat, and some people might be able to tell you exactly where you are, but I have absolutely no idea which slide this is specifically because it doesn't match mine. Okay, so no problem. But if anybody knows, type it in the chat for them. Okay. And again, with these slides, they don't all exactly match because sometimes there's a lot of extra I put in the PowerPoints that you don't necessarily have in your slides, and vice versa. Okay, so remember, for a precipitation reaction to occur, you have to have a solid. If there's no solid, then nothing happened, right? Nothing happened at all. Okay, so let's try this one. Now this one, again, so these reactions are actually so fun. So you can see here, this is a colorless liquid. Look, there's no color in this liquid right here, right? There's no color. And then this had no color. But when you put them together, it makes a nice orange precipitate. That's the precipitate. And we're actually going to be doing a bunch of these reactions. So they're actually really cool. So you got a clear colorless liquid, put them together, you make an orange solid, right? That's what a precipitation reaction looks like when we're doing it in lab. Again, you can see here, this is what you would see on a quiz or exam. This would be given to you, and I just give you that. And then you have to figure out what happens. So let's walk through this before I ask you to do all these yourself, and I'll try to write this so there's enough room. So lead, remember this 2 is the charge. It's not saying we have 2 leads, it's saying lead's charge is 2. Nitrate, polyatomic ion, potassium +1, iodine -1. So this is going to be Pb NO3 2 plus Ki. And then we need to flip our anions. So we have Pb plus I. Okay, so really important here before I go on. The reason this 2 is here is because lead's charge is a +2 and nitrate is a -1. That's why the 2 is there, right? We don't take this 2 over here necessarily, right? It's there to balance this specific compound, right? So we don't take it over unless we just don't take it over unless we need to, if it like happens to be. So if we do this one, we have Pb, and this time we have lead iodide. And then I put the I into the K here, sorry. And potassium nitrate. So I suggest before we go and figure out and balance everything, let's just see if we make a solid. In this case, I'm saying we do make a solid, right? But a lot of times what people do is they'll balance everything out and they'll balance the equation and they'll spend 5 minutes doing that and they'll look at the solubility table and the answer is no reaction. And you just spent 5 minutes doing all that work that you didn't need to do. So let's just make sure there's a reaction. Again, a reaction means there's a solid form. So let's look. All nitrates are soluble. We don't need to look at that one. Let's look at this one. Again, I like to look at the second one. It just works better. There it is right there. Iodides are soluble. That's an AQ, except silver, mercury. Oh, there's that lead too. So that means that this is a solid. So we have to continue on and finish this. Okay, lead was a +2 here. It's still a +2 here. Iodine's a -1. So we need to put a 2 there. And then we need to make sure we balance it. And again, you can balance this however you'd like. Whatever method works best for you. And so I just put an AQ instead of a solid, sorry. That would be your final answer. So again, it's using everything we did do with all of our new stuff. The only new thing really here is that when you identify it as a double displacement reaction, you need to look at the solubility table to see if one of these products are solid, right? So remember, this right here is actually just Pb, 2 plus floating around, and we have 2 nitrates, right? They're just floating around. That's supposed to be a 3. We've got this K, 2 Ks, they're just floating around. 2 Is, they're just floating around. Again, there's 2 Ks, they're just floating around. And 2 NO3s, they're just floating around, right? They're all AQs. I'm just not going to put AQs after them, except for this. This is not floating around, right? In this clear, colorless piece here, those are all the ions floating around. This is our solid, right? That's our solid. Everything else just floating around, not doing anything, right? It's our solid. That's what made the reaction occur. Let's have that illuminator for you. There you go. Much neater than I write. Okay, so these are double displacement reactions. Again, if you have a precipitation reaction, there has to be a solid. That is the key, right? That's their number one. There has to be a solid, or your answer is no reaction and you don't have to do the rest of the work. Okay. All right, so I want you, and I just gave you a different solubility table just so you can see that there's all different ones, to try this one. And if there's a solid, I want to know what the solid is. So try this one on your own. Great practice for your exam. Even if you're watching this later, please try this now. And then again, if there's a solid, I want to know what the solid is. So you can type in the chat or put it on your paper, and then we will go over it, and I'll give you like 2 minutes to try this one. And then we'll go over it together. Okay, so you should have gotten at least the first part of this done. So you're kind of seeing that this process takes a little while and it takes a lot of practice. Remember when I've done this, I've literally probably done 1,000 precipitation reactions. So when I do them, you're like, oh yeah, I can do that. You don't know that until you actually try it for yourself. So it's very, very important that you're trying these on your own, because I don't know if you've ever experienced when you see someone try something, like a professor, try something, you're like, oh, I could do that. Then you try it on your own and you're like, what? Right? So we want to prevent that from happening as much as possible. So make sure you're trying these on your own so you can see what you do and what you don't know. So then we can fill in all the holes and the blanks so you're ready for your quizzes and your exams. All right, again, lead 2 nitrate. So I'm just going to assume, by the way, that you all know this now. If you want me to explain any of those, let me know. Okay, so I'm going to try and be neater here. Lead goes first. K stays first. Lead goes with, I didn't leave enough room. I'm going to write this smaller. I'm going to switch these second ones. Remember, I am not taking this with me. The reason this 2 here, this 2 is because lead is a +2, nitrate's a -1. That is why the 2 is there, right? This 2 is here because potassium is a +1, chromate is a -2. That's why this 2 is here. I'm not taking it to the other side with me. It was just there to balance that one piece of the reaction. Okay, so now when I do this, potassium, lead is still a +2, chromate's still a -2, so I don't need to add anything. This is a +1, this is a -1. The charges never change, right? So we're good with that. Now, all nitrates are soluble. AQ. All nitrates are soluble. See, this is why this one's such a good one to memorize, because you don't need to look at a table for it. All right, and we gotta look at these chromates. So we go down here, here's chromate. Most chromates are insoluble. Remember, insoluble means solid, except NaK. Oh, there's our K, so this is obviously gonna be innocuous, right? And we don't have any of those other exceptions, so this must be our solid. Try to write this a little neater. That must be our solid, right? And then we have to balance it. It's actually kind of a nice balance. Put a 2 here. That's supposed to be a 2, right? So that's how we do our double displacement reactions. And so in this case, this is the one that made the solid. The rest of those, they're just floating around, not doing anything at all, right? That is our actual solid. Okay, any questions about anything on this problem?
Yeah, I have a question. Looking at the solubility rules on the table that you said you'd put on our quiz doesn't address chromate.
Right, so if you Google solubility rules, you'll see like a page, like so many of them, it's almost mind-boggling. So what we've done as the chemistry department we've only selected the ones that we've decided we're going to use. This, as you can see, is many more rules than the one that I gave you. So I just wouldn't give you one with chromates on a test or an exam. So,
gotcha. Okay.
Yeah. And if you want to look at all the solubility rules, it's kind of mind-boggling how many there are. But you're not, number one, you don't have to memorize any of them. So you'll never need to memorize them. But the one that I'm going to give you on the exam is just going to be the shortened one. Those are just the ones that we use just to make it easier so you don't have to look at them. Okay.
And those rules, the rules from your printout will also apply to the homework?
The homework, they actually, you'll see, have their own solubility rules. They have way more on theirs. So they have,
Chem 101?
Yeah, there's way more they use on Chem 101. So, and you'll see if you look, they have like, when you go through it, they'll actually have like a list of solubility rules for you. But you can also Google them, or I suggest this one. That was not an arrow. This pretty much covers like 95% of the solubility rules, besides the weird exceptions. So when you're doing Chem 101, you might want to have this one handy. just because it's more. And I also, like I said, really like this one. So if you're really bad with those polyatomic ions, you can use this solubility table to help you with your polyatomic ions, right? So like, for example, if you don't remember that's phosphate right there, it says it right here that it's phosphate, right? So this one's kind of nice because it helps. Okay,
Thank you.
no problem. So here we are. Again, this is everything we just did, just neater. So this would be your final answer. It would be this beautiful balanced equation. Okay, so now that's our double displacement reactions. Here's another one. And I think this one I gave you a bigger solubility table, again, because you might need it. So let's try this one. This one's even a little more challenging, which I'm gonna have an interesting place writing this. So try this one, and then we're gonna do this together in like 2 minutes. And again, this one's great practice for your exam also. Okay, I'm seeing a bunch of them come in. All right, so again, great practice for our exam. Cadmium is 2, means it's +2. Nitrate, -1, that's supposed to be a 2. And sodium sulfide. So I think I'm going to write this over here. So we have cadmium, 2, nitrate, plus sodium sulfide. And again, hopefully we're all really good with what I just did, because that's exactly what we've been working on. Keep cadmium first, keep Na first, and then I'm going to flip them. So it's going to be cadmium goes with sulfide, Na goes with nitrate. My charges are still the same. This is a +2, that is a -2, so I don't need to do anything with that. This is a +1, that is a -1, so I don't need to do anything with that. Okay, so all nitrates are soluble. I don't even need to look. I just know that one. So again, when you're doing these solubility tables, I like to look at the anions, just makes your life easier. Also, sometimes we look at the solubility table for our reactants and our products, but if it says solution, solution means AQ. That's literally what the word solution means. It means something's dissolved in water. So since it says solutions up, I don't even need to look. It's telling me that's an AQ because it's a solution. Solution means AQ. So I just need to look for this cadmium sulfide. So here's an S. Let's read this one. Sulfides are insoluble. Remember, insoluble, that means solid, except NaK, NH4+, or alkaline earth metals, right? That's group 2. Again, great review for a final. I can spell group, but not right now. That's supposed to say group. So that for cadmium is none of those things. So this must be our solid, right? So cadmium must be our solid. So very good. I see lots of those that come through. And oh, we have to balance it, right? So when we balance it, we have a nitrate. We have a 2 here, and then we are balanced. Okay, so here it is, much nicer. And here's what we ended up with in the end. Okay, so again, that's our double displacement reactions. Now, what we've been doing, this reaction, this is called a molecular equation. That's just what we call every equation that we've been writing so far. So far, this entire chapter, this entire module, have been molecular equations, right? We're going to learn, and we've kind of been alluding to this, how to break these molecular equations up. Remember, this S never breaks up. It's stuck together, right? It's like super glued together. The rest of these AQs, they all break up. So this molecular equation, right, we wrote this one. Again, that's what we've been writing, right? Remember, these are going to break up. They're not going to break up yet, but they will in a second. So that's our molecular equation. An ionic equation, or what we call a complete ionic equation, is when we actually break everything up. And remember, we're not going to break the solid up because it's super glued together. The rest of them are floating around, hanging out, not really doing anything, right? But the solid, sticking together, right? That's the one thing that doesn't break up. But if it says AQ, it means it can break up. And again, those insoluble compounds don't break up. All of the ones that what we're going to talk about aren't involved in our reaction, we call those spectators. So we're going to look at these equations. So this one is called complete ionic. And then we're going to look at our spectator ions. Okay, so how can you figure out what a spectator ion is? Treat your equation like you have before as kind of like a math equation. So it's almost like this side equals this side. Whatever is the same on both sides, we cross out. So if you look over here, see how there's a nitrate and a nitrate? So they are the same, so we can cross them off. See how there's an Na and an Na? They are the same, so we can cross them off, right? And so all that's left is what we call our net ionic equation, right? So our net ionic equation is what actually, sorry, let me go back, is what actually happened in the reaction. It's our actual reaction. So we have our molecular equation, which we've now written at least 20 times, right? Our complete ionic equation, that's when we break everything up. And then our net ionic equation is what actually happened. So let's do this one more time, and then I'm gonna have you practice. Okay, so here is our molecular equation. I didn't even make you like do the rest of it. So this is the molecular equation, right? Our precipitate, this is the one that doesn't come apart. It's our solid. Everything else comes apart, right? This PB is actually PB2 plus. This is actually 2 nitrates. This is 2 NAs. This is 2 I minuses. This again is 2 NAs. And this breaks up into 2 NO3 minuses, right? And so when we do this, now I'm just gonna write all of those out. Okay. So here I am writing all those out. So I just expanded it, right? So here's this PB2 plus. Now, why is it a 2 plus? Again, this is, think of it, here's this plus 2, and this is a minus. And it's actually, this plus is very important. This is very important that we actually have the plus here, right? Because it's an ion, right? So it's an ion, so we need to make sure lead as a solid is very different than lead as an ion, right? So for example, let's just look at sodium. Sodium as a metal, this, if you put this in water, it burns, it explodes, right? Very dangerous. But as an ion, doesn't really do anything. Just kind of hangs out, not dangerous at all to us. So it's very, very, very important that you have those pluses and minuses. And we're going to develop the why behind that. We're going to spend all semester doing that. But these ions are important. So these are all AQs. So if I don't have anything behind it, it's an AQ. I just didn't have any room. These are all AQs. But I put a solid, an S here, because the solid is very important. The rest of them are just all AQs. Now we cross off everything that's the same. So you see how there's 2 nitrates, 2 nitrates, 2 NAs, 2 NAs. And now the lead and the iodine, those are the 2 things that made this. That is going to be our net ionic equation. And our spectator ions are the ones we crossed off. So we crossed off the Na and the NO3, so there are spectators. Just like when you watch like a sporting event, the ones in the stands, those are the spectators. And so, hold on one second. So those are gonna be our spectators. So I'm gonna have you try, try this one, and then we're gonna go over it together. So I just want the net ionic equation, then we're gonna go over this. Okay, so I'm going to walk us through all three pieces, and then we're going to get to our net ionic. So first I'm going to do the complete, or I'm sorry, we'll do the molecular equation. So when we do our molecular equation, on one second, so you can see me. So when we do this molecular equation, it's silver nitrate. So this is nothing new. This is what we just, well, it's new today a little bit, and sodium chloride. And then we switch our two anions. So we have silver chloride and sodium nitrate. And then we look at our solubility table. This is our solid. This is our AQ. Sorry, I'm trying to write neatly. And this is our other AQ. And this is an AQ and AQ. Okay, this is our molecular equation. Now I'm going to split everything up that's not a solid. So I suggest, so you remember how to do this, you put like a box or something around your solid. So you remind yourself, don't take it apart, leave it together. We're going to take everything else apart because they are all just floating around in our solution. So this means it's going to come apart into Ag plus NO3 minus Na plus Cl minus, what's in the box stays together. This comes apart, Na plus NO3 minus. Now everything is AQ without the solid. I just don't have enough room to write it, but they're all AQs except for our solid. This is called our complete ionic. Now we're going to cross off everything that's exactly the same on both sides. Na, Na, NO3, NO3. And then we're just going to write the rest of these down here. Ag plus Cl minus makes AgCl solid. This is our net ionic equation. Okay, right? So it's a little like formula. So if we want to know like what actually happened in the reaction, this is what actually happened in the reaction. The rest of this is just extra stuff. This is what actually happened. So if you're taking 219 or 229, like in 229, we only deal in net ionic equations. That's all we deal with is net ionic equation because it's actually what's happening in the reaction. So again, this is net ionic equations. Now, if I ask you what the spectators are the ones you crossed off. We crossed off Na and we crossed off NO3. Those are our spectators.
So for Cl, we don't put Cl2?
No, because it's in water. Very good question. So our Brinkelhoffs, ClHOF, this is not in water. That's when they're gases. But if it's in water, then it's just AQ.
Thank you.
You're welcome. Great question. And this is an ion also, which is different than Cl2, right? That's a molecular compound where this is an ion itself. But great question. Okay. So again, this is how we do our molecular, complete, and net ionic. So when you're doing your homework, because I saw some of you are doing your homework, if it asks you for a dissociation is sort of like a net ionic equation. So for example, if it asked for the dissociation of like AgNO3, see how we did that right here? We broke it up into Ag plus and NO3 minus. That's what a dissociation is. We're taking it apart. So if you see on Chem 101, it asks for you the dissociation. It's just asking you to take the ions or the ionic compounds apart. That's what a dissociation is.